Today we're going to talk about bond enthalpy, and remember enthalpy is just the energy change associated with the process. So when we talk about bond enthalpy, we're talking about the energy change that's associated with the making or breaking of bonds. Just as a reminder, it takes energy to break a bond, but energy is released when a bond forms. So that idea makes bond enthalpy a little bit goofy to think about because really it can go in either direction. When you refer to bond enthalpy, I can be referring to the energy required to break a bond. So that means energy is going into a substance to break the bonds apart. So that would be an endothermic process. Or that same bond enthalpy can actually be referring to the energy that is released when a bond forms. And that would, of course, be the exothermic process. In either case, the number, the value is the same. The energy that is required to break something's bond is also the energy that that bond released when that bond formed. So to look at an example, we can consider a CH bond. This is not like a molecule or anything. This is literally just one carbon attached to one hydrogen. That carbon to hydrogen bond has a bond enthalpy of 413 kilojoules per mole. So you have two different ways we can interpret this. We can be interpreting that as 413 kilojoules are needed to break 1 mole of CH bonds, or 413 kilojoules is released when 1 mole of CH bond forms. Either direction, the bond enthalpy can refer to either, so it's really important that you understand whether we're making or breaking bonds in a given moment. For this next one, consider this reaction. This is methane combusting to make water and CO2. So some good reasoning here would tell us this is exothermic because we know methane is combusting and that should be an exothermic process. So let's go ahead and draw an energy diagram, just kind of brainstorming that idea here. We know this is going to be exothermic, so wherever we start, we'll have an activation energy, but we will end up at a lower energy state than we were at the beginning. But think about this. Let's draw carbon in red, hydrogen in blue, and oxygen in green. And oxygen appears in both of those. If I think about the reactants that I had here at this beginning phase, or this beginning portion, I have a CH4, which I'm actually going to try to draw for you. Not very well, but we'll see how it goes. 1, 2, 3, 4. Pretend those are all together. We also have an O2. Actually, we have two O2s, so we'll need two O2s connecting right there, and another O2 connecting right there. At the end of this reaction, we're going to have a water, which will look something like this. Actually, we'll have two waters. Pretend those are together. And then we'll have a carbon dioxide, which will look something like that. Well, in order to get there, these reactant particles must all separate out. So during this activation energy phase, we can think of it, all of these atoms have completely separated out. So we have our 1 carbon and our 4 hydrogens completely separate, and then we have our 4 oxygens completely separate. We had to break these bonds to get here. That means energy had to come in. But then we made bonds to get here. So that means energy had to come out. Well, there must be net energy loss here since this is exothermic. So that tells me this value must be greater than this value of bond enthalpies. But let's try to work our way there. So if you look at your 6.7 notes, or you can Google this, or on your test, it will be provided to you in the problem. We can look up charts of bond enthalpies, and we will find that on that chart, a carbon to hydrogen, which was on the last slide, has a bond enthalpy of 413 kilojoules per mole. Now we need to be careful here. This oxygen, this diatomic oxygen, is actually double bonded, so we're not breaking an O single bond, we're breaking an OO double bond, and we know it's more difficult to break a double bond than it is to break a single bond. Well, that bond enthalpy is 495 kilojoules per mole. But then over here in this water, right here and right here, we actually formed HO bonds. We formed a total of 4 of them, though, because there's, well, let me get that out of the way. We formed OH bonds, but there's 2 OH bonds here plus 2 OH bonds there for a total of 4 HO bonds or OH bonds, which happen to have a bond enthalpy of 463 kilojoules per mole. And again, these bond enthalpies would be provided. You don't have to memorize them. Then we have a CO bond, but if you think about the Lewis structure for CO2, it's actually a double bond, and there's two of them, but we'll address that in a moment. A CO double bond has a bond enthalpy of 799 kilojoules per mole. And just to point out, we would have expected these two right here to have the highest bond enthalpy because they're double bonds, and they do, so that's good. But we did not just break one carbon to hydrogen bond here. We broke a total of 4 of them within this one molecule. So we need to multiply this number by 4 in order to determine the energy input there. And that equals 1652. Here for the O2, there's a double bond here and a double bond there, so there's 2 double bonds occurring that we're having to break. So multiply this one by 2, that's 990 kilojoules. Then over here, the HO bonds that we're forming in the water, again, there's 2 HO bonds in each one of these waters. So really we're forming 4 of these. Well, 463 times 4 is 1852. And then on the CO, you're forming 2 different CO double bonds within that CO2. So we'll multiply 799 times 2, and that equals 1598. So what we can do here, though, since we know the total energy that's going in to break these bonds, let's go ahead and add those together. So we're going to take, there we go, we're going to take 1652 plus 990, and this is representing the energy that's going in, for a grand total of 2642. Then if we'll take these two, which are the bonds being formed, this will be energy out, because energy is released as those bonds form. So that's 1852 plus 1598 for a grand total coming out of 3450. So right off the bat, we can conclude that we were correct when we assumed this was exothermic, because you have 2642 going in, but 3450 coming out. There's a net exit of heat from this system, so this should be exothermic. In order to find that difference, we just need this very simple equation, which actually is not on your formula sheet, so it's almost easier just to think about without the equation. But we can find the enthalpy change of this entire reaction by adding together the bond enthalpies of what was broken minus adding together the bond enthalpies of what formed. This capital sigma here just means the sum of, so we're just adding together, and we actually already did that. Going back, we know that when you added these together, 2642 went in, and 3450 came out, so minus 3450, and what you've actually just calculated is the total enthalpy change for that reaction. The total enthalpy change of this reaction turns out to be negative 808, and our units there are kilojoules per mole. So because more energy came out than went in, we knew this was exothermic, and it was exothermic to the degree of negative 808 kilojoules per mole.